Welcome to this Ansys How-To series video. Today, let's talk about buckling analysis. So why is buckling important to study for engineered structure? Buckling usually involves a sudden loss of stiffness of structure and also drastic deformation change. A couple of examples include the break of a wind turbine column after a storm or the drastic distortion of train rails due to high temperature. We may also see local buckling, where buckling occurs in an isolated region, allowing the structure to still support the load. For example, the dents on the shell of a fluid tank or the distortion of the flange of a steel beam are such cases. However, buckling is not always related to failures or tragedies. Sometimes, buckling is part of the engineered design. The foldable laundry basket and foldable silicone bowls are examples where the buckling mechanism is well utilized for our convenience. In mechanical simulation, there are multiple routes that engineers can take to perform buckling analysis on a structure. Among these methods, Eigenbuckling analysis is the most efficient way to predict buckling loads and understand all possible buckling modes. So it serves as a critical first step in any study on instability. Now, let's get started and learn about eigenbuckling analysis. First of all, we should notice that buckling is a highly nonlinear process. Sometimes it even involves a snap-through phenomenon, which means the displacement jumps from one configuration to another, even without an increase of the applied load. Solving the entire buckling behavior of a structure can be challenging and computationally expensive. Eigenvalue buckling analysis avoids the complexity of solving a nonlinear system. It solves a linear set of equations, allowing us to predict the theoretical buckling strengths of an ideal elastic structure. This method corresponds to the textbook approach to an elastic buckling analysis. For instance, an eigenvalue buckling analysis of a column matched the classical Euler solution. The benefit of using this approach is that it is computationally efficient. It gives us a rough estimate of the buckling loads, and it gives us an idea whether or not there's more than one way in which the structure can buckle. However, we should keep in mind that the eigenbuckling results are unconservative since they do not include any nonlinearities that real-world structures experience. Thus, we often view eigenvalue buckling analysis as an important first step in examining designs that may experience buckling. Eigenbuckling analysis is based on a classic eigenvalue problem and uses linear perturbation method. So what is the linear perturbation method? The linear perturbation analysis procedure is designed to solve a linear problem based on its prior linear or nonlinear preloaded status. We call the prior linear or nonlinear analysis the base analysis. The perturbation analysis freezes the effect from the base analysis for reuse in the current or future analysis scenarios. Here, we're looking at the governing equation of the eigenvalue problem for eigenbuckling analysis. Just like all classic eigenvalue problems, the equation solves for eigenvalues lambda and eigenvectors phi. We'll talk about lambda and phi a little bit later. Let's first look at the KT matrix and S matrix. We should note that the KT matrix may be the total tangent matrix from the load point of interest instead of the initial total stiffness matrix. And S is the linear perturbated stress stiffening matrix. Stress stiffening is the stiffening of a structure due to its stress state. For example, a guitar string is tightened in tension to increase its frequency or pitch. Now, coming back to the unknowns in this equation, which are eigenvalue lambda and eigenvector phi. Here, the solved lambda turns out to be the load factor or buckling load magnitudes, and phi is the corresponding buckling modes. As the subscript I indicates, there may be more than one way in which the structure may buckle under the given loads, and engineers are usually interested in the first few buckling modes of a structure. Now, how should we understand the term load factor or buckling load magnitude? It's actually not the buckling load value. We will discuss this in two situations. First of all, when the base analysis is a linear analysis, the buckling load is computed by multiplying the applied loads by the buckling load factor. For linear-based eigenvalue buckling analysis, the perturbated load F perturbated equals the applied load in the base analysis. However, when the base analysis is nonlinear, for example, when material, geometric, or contact nonlinearities exist, the buckling load is calculated differently. In an eigenbuckling analysis with a nonlinear base state, we can define a different perturbation load in the buckling analysis compared with the applied loads in the nonlinear base analysis. Therefore, the load multiplier lambda scales only the loads applied in the buckling analysis. The total buckling loads is the sum of the load applied in the nonlinear base analysis and the scaled perturbation load. Note that if we set keep pre-stressed load pattern to be yes in the buckling analysis settings, the load applied in the base analysis will be used as the perturbated load in the buckling analysis, and we don't need to define a new load. And the total buckling load becomes this. We should pay special attention to the different ways of calculating the buckling load in eigenbuckling analysis based on either a linear or nonlinear analysis, as doing so incorrectly can lead to errors in evaluating the actual buckling load. Now, let's move on to a simple simulation example and learn how to do an eigenbuckling analysis in Ansys Mechanical. Here, we're looking at a column structure with a box-shaped cross-section. The four sides of the columns are modeled by surface bodies with assigned thickness. At the bottom of the column, the deformation in x, y, and z direction is fixed, while the rotations are free. At the top of the column, it's fixed in x and z direction, but free in y direction and all the rotations. A force is also applied on the top of the columns in the negative y direction. Such boundary conditions and load can be described by this sketch. Note that for linear-based eigenvalue buckling analysis, the value of the force does not affect the results, as the results will be the product of the load factor and the perturbation load. We'll prove this in the simulation. Here, let's make this force minus 5 times 10 to the 5 Newton for now. Since the material used in this simulation is linear, the large deflection formulation is turned off and there is no nonlinear contact. We know that this static structural analysis is purely linear. Solving this simulation, we can quickly review the deformation and equivalent stress results. Now, let's go back to the workbench schematic, drag an eigenvalue buckling analysis from the toolbox, hand it over the static structural analysis, making sure that the engineering data, geometry, model, and solution modules are covered and highlighted. Then release the mouse. Now the static structural analysis becomes the base analysis of the eigenvalue buckling analysis. Double-click on the setup of eigenvalue buckling analysis to open it in Mechanical. In the analysis settings, set the max mode to find to be 10. Then we're ready to solve this eigenvalue buckling problem. After the solution is complete, we can find that the 10 load multipliers listed here. Select all the rows and right mouse click and select Create Mode Shape Results. All of the buckling modes can be visualized. Note that the buckling mode shapes are relative values. By checking the first few buckling modes, we can get an idea of whether or not the structure can buckle in more than one way. In this case, the first two buckling modes are similar, though occur in two different directions. The load multiplier of the second buckling mode is about 1.5 times of the first buckling mode's load multiplier. Such a difference is caused by the difference in dimensions of the cross-section in the two directions. If the change in dimension is smaller, the second buckling mode may be triggered. We also see that the third buckling mode is 3 times larger than the first. So chances are low that the third buckling mode will be activated for the applied load. The buckling modes after the third one are associated with local buckling on the thin walls of the column. For this case, the local buckling modes have higher load multipliers, so this column may not experience local buckling along its walls. But in general, we can plot buckling mode shapes to understand whether or not the buckling is local or global. We should remember that the results we have here is load multiplier instead of the buckling load itself. To find out the buckling load for this linear-based eigenvalue problem, we need to multiply the applied load in Bayes analysis by the load multiplier. So for first buckling mode, the buckling load can be calculated like this. Now, let's go back to the Bayes analysis and change the value of the applied force to check if it will affect the buckling results. This time, we make the force -1 Newton. Solve the Bayes analysis and also the eigenvalue buckling analysis. We will find that the values of the obtained load multipliers have changed. But let's calculate the buckling load. For the first buckling load, it should be the applied load 1 Newton times the first load multiplier, which actually matched the buckling load we calculated for the previous case with larger applied load. Also, if we go through the buckling modes, they are all the same as the previous case. This proves that for eigenvalue buckling, the applied load in the linear Bayes analysis does not affect the buckling results. However, for nonlinear based eigenvalue buckling analysis, this is not the case, because we need to add the applied load in the nonlinear Bayes analysis with the scaled perturbated load in the eigenbuckling analysis. The proportional relationship is lost due to the summation of the two parts. In general, eigenbuckling analysis is a very efficient way to predict the buckling loads and associated buckling modes of a structure. It's an important first step in any study of instability or buckling. Although it's a linear analysis that calculates the unconservative theoretical buckling strengths, it provides us with information on whether or not there may be more than one way a structure can buckle. Being able to identify and review possible global and local buckling modes is also possible with this method. Such information cannot be obtained by a full nonlinear buckling analysis, as it only generates one buckling solution. Also, we can utilize eigenbuckling analysis results in preparing for nonlinear buckling analysis. For example, the obtained buckling load is a good approximation of the amount of load that should be applied for the nonlinear buckling analysis. Note that symmetric, idealized cat geometries may show little tendency to buckle in an asymmetric fashion. But the obtained eigenvalue buckling modes can be used to introduce an initial imperfection within manufacturing tolerances, for example, to help initiate buckling and provide more physically realistic results. Hope you enjoyed this video for eigenbuckling analysis. If you found this useful, please like and share the video and subscribe to the channel. Also, please visit ansys.com/courses to discover more useful contents.